Okay, welcome class. This is a supplemental video to today's lecture, which is Friday, 29th of October. So when we did the recording, I forgot that you couldn't see the coding part of the talk, only the slides. So I'm going to sort of redo the coding part. Okay, so what I'm going to do here is to go over how we built the fitting program. Okay, so what are we going to do here? We're going to actually fit a Michaelis-Menten curve. Okay, so we'll have some quote unquote experimental data, which will be noisy probably from experimental error, and I want to find the best KM and the best Vmax that matches that data. Okay, so I'll have that Michaelis-Menten curve, and I want it to fit that data as closely as possible, so that I can get good estimates for the Vmax and KM. So let's begin. So the first thing I'm going to do is import some libraries I'm going to need. lmfit, numpy. I'm pulling some things out here. I don't really need to do that, but I could just use np dot something, but no, not to worry. And then this is the matplotlib library. Okay. All right. So I'm going to see if I can type manually now instead of cut and pasting. So the first thing I'm going to do is define the function that we will fit, and that's just the Vmax one. So all this does is return the Michaelis-Menten, the value for the Michaelis-Menten equation. Okay, and that's it. That's all it does, right? So this is a function which I've called which stands for Michaelis-Menten, takes 3 arguments. First argument is the concentration of the substrate, and it's the second 2 arguments are the Vmax and Km. Okay, so I can call this. So if I run this, okay, I can actually call this, right? I could go 4.5, and the Vmax is 5.6. Maybe the Km is 3.4. Hit, oops, close the bracket, hit return, and I get a number. And that number is the reaction velocity at a concentration of 4.5 for the substrate. Okay, so now I don't actually have any experimental data, so I need to create some fake data. So that's what I'm going to do now. So first thing I'm going to construct are the X data points, okay? And I'm going to use something called, so I could actually use linspace directly. There we go. All right, linspace, there it is. I'll show you what this does in a minute. So let me run this. If I type X axis, gives you numbers. How many numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers, yeah. So it's from 0 to 20, 10 numbers, okay? So I guess if I did 11, I would get a much more even distribution, okay? In fact, let's do that in this case. So these are the substrate concentrations I have, all right, in my experiment, and I need to compute now what the experimental reaction velocities would be. Now, in order to create fake data, I have to assume some kind of ground truth, right? So there is an enzyme out there which has these characteristics, a Vmax of 5.6 and a Km of 2.3, right? Once I start fitting, I have to pretend I don't know these two, right? And the objective then is to find the values of these two. But in generating the experimental data, I obviously need to start off with some ground truth, and that's what I'm doing here. So I'm going to generate the experimental data. This is really easy to do. All I do is KM. Now, because I'm using NumPy, and my x-axis is a NumPy array, if I feed x-axis into this function, this function will be treated as a vector operation. So in fact, if I run this, okay, and then I ask it to print out the experimental data, you'll notice I get a vector. All right, so this thing has computed all the reactions velocities for me for all 10 substrate concentrations. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh yeah, that has to be 11 because you start from 0. Okay, so that's my experimental data. Now, that data, however, is perfect. There's no noise in it, so I need to add some noise. So let's compute some noise. So let's just do random. normal. So what this does is it generates normally distributed data, you know, the bell-shaped curve. I need to specify a mean. The mean is going to be 0, and then a standard deviation, and how many points I need, which is 11. So if I run this and ask you to print out the noise, I get those are my errors. And you notice they're negative and positive. That's because the errors can be above or below the reaction velocity. Now, to generate the actual experimental data that I'm going to use, all I have to do is take the experimental data and add the noise to it. Again, because these are all NumPy arrays, these are all vector operations. So all the numbers get added up. I don't need to use for loops or anything to work my way through the list in the array. All right, very convenient. So why don't we check now that this data sort of looks like experimental data, shall we? So let's plot it, shall we? X-axis and then experimental data. There you go. All right, and let's use a round symbol for that. So let's plot it. Here we go. And there you see, it looks pretty noisy, doesn't it? Yeah. If I run it again, I obviously get a different set. That looks much nicer, doesn't it? If I run it again, I get a different set. So each time I run this, I get a new set of experimental, quote unquote, experimental data. Okay, I'll comment this plot out. No, I don't need that anymore. Okay, so I'm ready now to do the fit. Okay, so the first thing I need to do is define my my function that's going to compute the residuals. Now, the funny thing about lmfit, and in fact, most of the fitting algorithms in Python, is they don't want you to compute the sums of the squares. All right, remember the sums of the squares was, I'll put it down here, sum, it was, just to get the right symbols right, experimental data minus the function itself, right? Function I, I all squared. Okay, that's what. So that was the chi-square. Okay, that was the chi-square. Right, that's what we would normally compute. Now, for some reason, the Python optimization libraries only require the middle piece, and in fact, they want an array of differences. So this difference here is actually the residual, and they want it for every I. So for our model, we have 11 data points, so there will be 11 residuals. Okay, so I need to compute this thing in the residual. Okay, now in order to do that, I obviously need access to the let me see the experimental data. So let me put that over here. That's going to be the experimental data. Experimental data. Okay, and I also need the concentrations that correspond to each of the elements in the experimental data. So what's going to happen is that the optimizer is going to repeatedly call this function, right? And P is the current values for the Vmax and the Km. Okay, so it'll use those to compute the residuals, but it needs access to the x-axis data you see on the plot on the right-hand side. It needs access to all those data points, and they come from x-axis and experimental data. Okay, so how do I compute the residuals then? Well, first of all, I'm going to, just for convenience, I'm going to pull out the actual values of the Kms and Vmaxes. Okay, so this is the Vmax, and then this is the Km. You'll see where this comes from in a minute. But I should point out that the P, when P comes in, it's a dictionary. Okay, so I'm just pulling out these values from the dictionary, and I'm assuming that the key to the dictionary is Vm and Km. All right. Next thing I'm going to do, I need to compute the function, that bit. So I'll call that, I want to call it fi then, all right, just for the sake of argument. And that'll be the x-axis. So this is calling the, I need to find out what the fitted function is at the current values of Vm and Vmax. So that's what I'm going to compute here. So it needs the x-axis, the current VM, and the current Km. Okay, and that gives me the function data, and then to compute the residuals, and I can return this in one fell swoop. I just take the fi. Well, I'll just do it this way. Don't think it matters which way around I do it. I'll take that and I will subtract from it fi. Okay, so basically computed this piece here. It doesn't want me to square it, and it doesn't want me to sum it. All right. It just wants the list of residuals. Okay. All right. Now, where does P come from? Okay, so this is where I have to start using lmfit, and I'm going to create a variable called called params. Okay, this is going to be an object that's going to store the parameters I'm going to use. And there's an add method that lets me add the name of the parameter, its initial value, and for our purpose, we also have to give it the bounds. So it'll never go below 0, and let's say it never goes above 20. Okay, so that's how I tell it about the Vmax, and I need then to tell it about the Km as well, of course. That's just the same bounds. All right. So you have to use your judgment here on the bounds. Obviously, these parameters can't go below 0, so the minimum must be 0. And we happen to know, because we know what the ground truth was, we know they don't exceed 20 because this one's 5.6 and one's 2.3. You could give really big bounds here and let it deal with it, but we give it narrow bounds because we know some information. Okay. Okay, so actually we're ready to do the fit, in fact. So let's do the fit. So lm fit minimize. Is it minimize or minimize? Minimize. There it is, minimize. Yeah. So it's giving me some clues here as to what it wants. The first thing it wants is the function that computes the residuals. All right. I suppose I can't spell here. Residual. I should call this plural, I think, plural residuals. The next thing he wanted were the parameters. Well, I have those here ready, and it's the same name. This bit here is anything extra you want to pass to the residuals. Now, normally residuals only expects P, but if you want to pass anything else, you can tag them on like that, but you have to tell it about what you're tagging on here, and you do that with the args. With the args argument. So I'm going to pass to it the x-axis and the experimental data. Okay, remember that's what it wants. That's what we're passing in, is the x-axis and the experimental data. Actually, I just realized, yeah, I spelled that wrong, didn't I? You probably spotted that before I did. That should be experimental data. Okay. Okay, and that's it. In fact, if I run that, just run it, nothing happens, of course. If I go result dot message, fit succeeded. Oh, good. So how can I get hold of this fit then? Well, you can do this thing for a start. You can write a report. There's a report thing here. That just wants the result. Okay, so if I run this, there you get a report. You see that report there on the right hand side? So it tells me a bunch of things. It tells me what the fitting method was. That's the default, which is least squares, which is the Liebenberg-Marquardt. How many times the residuals was called? 16 times. How many data points I had? How many parameters I had, which was 2? What was the chi-squared for this fit? What was the reduced chi-squared for this? These two things or at least this one, you'll come across next week. And then it actually tells me what the fit was. In fact, it doesn't look that good, actually. So the Vmax, it estimated at 4.8, when in fact, we know it should be 5.6. The Km was really badly fitted. 0.55, it thinks it is, but in fact, actual fact is 2.3, okay? This gives you some idea of the percentage error. So you can see the percentage error on the Km is quite high. Now, if I run this again, let me run this again. I want to show you what happens if I just run this bit again, run that. I get, if you look at the values, 4.844, 4.844, 0.5561, 0.5561, they're the same. The reason they're the same is that, of course, I'm using the same experimental data. I didn't regenerate that this time, right? I only ran this cell here. The second reason is that the Liebenberg-Marquardt optimization algorithm is what's called deterministic. That means if you run it again and again and again with the same inputs, you'll get the same output, all right? That's what it means. Now, if I were to run this whole thing again, I'll get a new set of experimental data, and I might get a better fit this time because the experimental data will be different. It might be, better. Let's see what happens. Yeah, that's better. Look, that's 3.2. Well, the error is still 32% though. That's still pretty bad as well. In fact, what we should do, we should start plotting things, I think. If I'm going to replot that, let's plot that again. So let's run this again. So this is the experimental data I used to get this information. And this is much better, actually. That's 2.7 when it should be 2.3. That's 5.4 when it should be 5.6. Still, the error on that is quite high. Let's run this again. See what we get. Oh yeah, this is pretty bad. You can see this is really noisy data. You see the errors, gone up. Now I can reduce the error in my experimental data just by not adding so much noise. And this thing here is the noise generating bit. So let's take this down to 0.2. So there's much less noise. Let's run that. Now you see the data is less noisy. And now you see the errors are down. That's good. I got 5.9 instead of 5.6 and 2.7 instead of 2.3. Let's go down even further. Let's go to 0.1. Yes. Oh, look, now the error is already dropping. Okay. So this is artificial, of course, because, I mean, who knows if you could get experimental data as good as this. But anyway, you can play around and do things like that. Now, one other thing I want to do is I want to plot some more stuff. So I'm plotting the experimental data there. I'd like to plot the fitted line. And the way I'm going to do that is I'm going to create a new set of, I want a nice smooth line, all right, for the fitted line. So I'm going to create a new set of x-axis data called x smooth, and that has 100 points on it, right? So if the data is only 11, right, which is why you only see 11 points here, but I want to generate 100 to make it smooth. Then I need to compute the fitted model. That is the data for the fitted model. The question is, how am I going to do that? Well, the way I do it is I need to know what the fitted parameters were. In this case, it was 5.48 and 2.02, and just plug it into this. And that will return me the fitted reaction velocities. How do I get hold of 5.48 and 2.02? Well, it's pretty easy. Let me just type this first. So that's x smooth, that's the x data. Now to get the fitted parameters, I take the result from here, right? And then I just ask it for the params. Give it the name of the parameter I want, Vmax first, and then value. Remember, don't forget the value. So that's the value of the Km, and then the value of the the value of the Vmax, and the value of the Km is just this one. Okay, value. All right. Do I need to close any brackets? No, that's the fitted model data. Now I need just to plot it. Okay, so plot x smooth and fitted model. Okay, all right, let's run it. There you go. So what you see in orange now is the fitted data, and it's nice and smooth, right? If I didn't make it smooth, let's say I made it, 11, which is the original resolution of the experimental data, you'll see the straight line segments, okay? It's basically joining up all the points, but I want to make it look smooth, so I'll give it 100. Now it looks smooth. That looks pretty good. In fact, if you look at it, the fitted Vmax is 5.6. That's really close to the actual value. And knuckles 2.299, that's pretty much dead on 2.3. That's why it looks so perfect. Okay, now let's bump up the the amount of noise, run it again. It's not surprising it doesn't do too well. You can see the data points are scattered, around the best line. The last thing I want to do, excuse me, the last thing I want to do is plot the residuals. And there's a little method in the matplotlib called v-lines that plots vertical lines. It'll plot vertical lines at the x-axis points. They will start from 0, and then they'll go up to this level. This level is the residual. It's the difference between my experimental data and the fitted model. The only issue here is that I've got the wrong dimensions now, because experimental data is 11 points, but I made some new nice smooth fitted data, which is 100, so that the data don't match. So I'm going to have to recreate that. So let me do it here. So I'll create that x-axis. Get that back. That should be 11. That stays the same. Now I can run it. Oops, what did I do wrong? Oh, missing bracket. There you go. Oh, and I've still got the wrong shape. What did I do wrong here? Oh, yeah, this is wrong. Wrong name here. Okay, that'll be better. There you go. So these lines here that you see on the x-axis, those are the residuals, all right? And you can see that these two data points here, they're far away from the line, so they have big values. One's negative, the other's positive. If I run this again, different set of experimental data, I get, another set of residuals. Okay, so that's how I did a basic fit. Just one other thing I want to mention here. I'm going to make a copy of the minimizer, right? And I'm going to show you how I can specify, oops, get out of the way, specify a different optimizer. So I'm going to put in differential evolution, right? That I'm engaging a different optimizer. Comment that out. Now run this. I get another one. This is now using the differential evolution. Notice there's no error estimates on the Vmaxes and Kms anymore. Notice up here, maybe I didn't say it, but there are error estimates on them, plus or minus error estimates. I think these are 95% confidence limits, but you'd have to look at the documentation to check. The other one I can try is Nelda, for the Nelda mead. Right. So what you do in practice, you'd try all these to see which one has worked for you, okay, your data and your model. But it's easy to work your way through them. Okay, I think that's it. I don't think there was anything else I wanted to say. I mean, I can show you what happens when you give it, crazy error, crazy amount of noise. You get that, which doesn't exactly work. Although it's tried out a good stab at getting the Vmax, although Km is way off. So if I put it at 0, of course, that's perfect data. I get perfect data, right? 5.5999999, 2.300. Okay, so it's perfect data. Notice all the costs of the chi-squared, tiny. That shows you how good the fit is, all right? Okay, I think that's it then, all right? If you have any questions, send them to me on Slack, and I'll answer them there for you. All right, I'll upload this to YouTube, okay? And then I'll send you the link in 10, 15 minutes. YouTube takes a while to process videos. Okay, bye now.